appreciate that. Jonathan's one of them. Liam back here at the back is one of them as well. So with that, I think, Jonathan, whenever you're ready, I think we've got like 1 minute until 6:45, and then we can start. So,
perfect. If I am multitasking here a bit, it's because, like you said, I also do the live streams for the section, so I'm trying to do that simultaneously here. Okay, so like you said, I am a PhD candidate here at Mayo Clinic. I did my undergrad at St. Olaf before starting here in 2019. And my research focuses on magnetic resonance elastography, a very specific problem to one imaging modality. But I rely very heavily on the use of neural networks and AI in that research, and have a pretty good sense of how they can be used generally. So I put together this talk, and supposed to get started here, I just wanted to go over a couple of definitions so that we're sort of on the same page when we're talking about terms like AI, neural nets, machine learning, and deep learning. So the first of these is machine learning, and I am not going to read this. I copied this definition off of Wikipedia, but the issue with a lot of these definitions is that people don't really agree on them. So if you're reading in the news one person's use of the words, they might not line up with another person's use of the words. For example, here we have these two diagrams. These very clearly disagree with each other. One of them puts machine learning as being entirely encompassed inside of AI, and the other has machine learning being much larger than AI with only some overlap. These are from the exact same Wikipedia page. They are just listed right next to each other. So when you look up online the definitions for these, you are going to get a lot of mixed results and people not agreeing, and that's because there isn't really consensus, and a lot of this is sort of a gray area when we're talking about one versus the other. So my sort of fast and loose definitions for these are machine learning. Anytime we're training a computer, I do want to specifically say I include analog computers with this, as there are individuals doing AI work on analog-based systems. This definition that I use for machine learning likely means that everybody in this room has done machine learning. Apologize. If you have ever used a line of best fit, put some data in Excel, have it draw a line of best fit, that would be a form of machine learning based on this definition. And if we look at this diagram here, that's what this is trying to encompass as well. There you are having a computer learn from your data what line is going to fit it best, and then you can use that to make predictions about where additional points would fall. In addition then, things like deep learning, neural networks would also fall under this definition. So machine learning can be a very, very broad topic. The next one then to discuss would be, what is a neural network? A neural network is an algorithm or a set of algorithms designed to mimic neurons. So you also hear these referred to as artificial neural networks. Oftentimes we leave the artificial off, but we're talking about the same thing. We, computer scientists, decades ago, before I was born, started realizing that one of the most powerful ways we could create computer programs is to base them on the one thing that we knew functioned, which was brains and neurons. So here I just have an example drawing of what a simple neural network would look like. We have a couple of different inputs. We have what's referred to as a hidden layer. This is hidden because you generally don't see it. You know what your inputs are, you know what your outputs are, but you're not looking at every layer in the middle. The way this is designed to mimic neurons is that each one of these nodes has an activation energy that's required, or some activation value that's required in order for it to send a signal to the next one down the line. The strength of the signal that gets sent is represented here by the thickness of the arrows. So for this first node in the hidden layer, it has a fairly weak connection to our output. So that would signify something that isn't overly important in our model. By comparison, the second node has a much stronger connection to our output. So that would be a feature that's much more important to actually predicting our output successfully. Deep learning then is just more neurons. The deep part of deep learning simply refers to the depth of the neural network that's being used. So where exactly you transition from neural networks to deep learning is, again, one of those gray things that's not perfectly agreed upon. And I did my best to draw this. I don't think I forgot any arrows, but obviously as you add additional neurons, this becomes increasingly difficult. When we look at an example later during the coding demo section, we'll have a neural network that utilizes much more than 4 of these per hidden layer, up to, I think my default, I start at 10. When I'm doing my actual research on more complex problems, we normally start at 100 filters per hidden layer. So you can take each one of these and instead of having them be 4 tall, make those all 100 tall, and then imagine how many connections would be required between all of those neurons. And then lastly, AI or artificial intelligence. I underlined the part of this that seems important from my perspective, the perceiving, synthesizing, and inferring information. Again, this becomes really gray as to where we say, okay, this is a deep learning algorithm, but now this one's AI. Even since I started in working with AI back in about 2018, 2019, which is not very long ago, this target's moved a lot. From just a few years ago, basically nobody was using AI to describe what we were doing. That was reserved for the robots you could actually talk to. And now we seem to be using AI to describe a lot of the same algorithms that we weren't describing with the term AI just a few years ago. So then why do we want to use AI? Why AI instead of some other conventional algorithm that we can understand that isn't a black box? Well, there's 2 primary reasons. The first of which is that we don't have another option. Oftentimes, we're trying to solve problems that are previously unsolved, things that there aren't conventional algorithms designed to solve, or systems that are too complex for anybody to produce a conventional algorithm for. In these cases, AI might be your only ability to tackle the problem or tackle the data set. The other reason, and there's been an increasing amount of research into this in the last probably just 1 to 2 years, artificial intelligence or neural nets or whatever we want to call them can be more efficient than a traditional algorithm, especially when we look at the new hardware acceleration units for them. Oftentimes, AI can outperform as well as be more energy and time efficient than a traditional algorithm at the same task. Okay, so like I promised, I will get to some coding examples where we can see some specific AI structure. But first, I want to run through a little bit of background on my research, as well as cover the topic of why I started using AI and why it's fundamental for the work I do in medical imaging. So the first thing to discuss is magnetic resonance elastography. There's a good chance a lot of you have heard of magnetic resonance imaging, or MRI. Magnetic resonance elastography is a similar concept. We actually use traditional MRI scanners and traditional MRI sequences, but with the goal of trying to determine material properties like stiffness inside of areas that a doctor couldn't normally reach, like the brain. So the primary reason for this is we've known for a lot of years that a lot of different diseases can affect the stiffness of tissue. This is why when you go in for a physical, the doctors poke and prod lots of different parts of your body, feeling for lumps and things that they don't want to feel. But there are areas where we simply can't feel, like the brain, or can't feel precisely, like the liver. And MRE gives us a tool to look at that same material property doctors have been feeling for millennia now, which is tissue stiffness, but do it in a non-invasive way and do it on tissues that we can't visibly, or we can't see or physically touch, like the brain here. So the way this works is a device called a driver, which is one of these here, Normally, it actually goes behind the head during a lot of conventional MRE exams, and it is basically an inflatable pillow. And then a pneumatic system pulses air into that pillow 60 times a second. So it generates 60 hertz vibrations, and those travel into the soft tissue, and we can image that using a specific type of MRI sequence. And we get these nice wave images here of waves propagating into your soft tissue from, in the case of the brain, they often look like they're propagating in from your skull. We can see sort of a simulated, actually this is not a simulated, this is a real example here of waves propagating through a phantom from our driver, and then using what we call inversion, which is the process of going from these wave images here to a stiffness map. We can see where these inclusions are. I don't know, it looks like they're maybe slightly visible, but on the conventional MRI image, we have something that's very difficult to see, and using MRE, we get something that's very easy to see. This can be exceptionally important in cases where we want to know stuff like the stiffness of a tumor. So while these are obviously tumors in the brain scan, we also see increased stiffness in the MRE exam. And this can be very important for surgeons to know when going in to operate how stiff that tumor is going to be. I'm going to go over this section very quickly, the mathematics behind stiffness. So in general, we express stiffness as this 6x6 stiffness matrix that relates strains and stresses to each other. When we're handling this in simulations, this is what we need to implement mathematically. That's all the time I'm really going to spend on that. Okay, wait, I might have kind of lied. Circling back to inversion then. What does inversion do? Well, inversion gets us from wave images to some numerical quantity we care about. But the inversion you've seen so far, that one example I showed of the two cylinders, that's using a process called direct inversion. And direct inversion is a classic analytical solution to a problem. We have this equation here. We can plug in variables like material density, the frequency of the waves, which we know because we control that. The U here is the wave images that we recorded. And then we get out this value in stiffness, which is that map I showed earlier. The problem with this is this version of the stiffness matrix has a lot of assumptions in it. In fact, we've gone from a 6x6 stiffness matrix of 36 total possible values down to one that has only two values, the mu and lambda parameters. All the other terms just relate to each other. And this works. We can take wave images and we can use DI and we get these elastograms or maps of stiffness. But neural nets present another potential way to handle this same problem. If we could train a neural net that looks at wave images and can technically not calculate the background or the stiffness of the material, but estimate that stiffness based on other waves it's seen, we could use wave images and then get a neural net to give us the stiffness map that we've been getting from direct inversion for the last about 3 decades now. And we can see in an example here where using this phantom with stiff inclusions, once again not visible on conventional MRI, we can start seeing some of the larger ones with the analytical solution or direct inversion, but that AI can actually outperform the analytical solution. And one of the reasons is we can start getting rid of assumptions. So for example here, we see that this is inhomogeneous training data. That means the neural net doesn't assume the two voxels next to each other need to be similar or the same in any way. And that's something that direct inversion is forced to do in order for us to get that analytic solution that we can actually write out. So by eliminating simplifications that allow us to get to the analytical solution, we can get much better results. but now we're being forced to use something like a neural network in order to handle that inversion step. And my research takes that even a step further, moving away from isotropic material properties, meaning materials that look the same in all directions, and moving towards anisotropic material, meaning parameters can be different depending on what direction you're looking at the material in. If anybody has a fleece blanket at home, then you're probably familiar with anisotropic materials. If you take fleece and you try to stretch it in one direction, you'll find that it's stiff and doesn't move. But if you try stretching it at 90 degrees, you'll find that it stretches quite a bit. That's because it's made out of fibers, and in general, anything with fibers is going to act like an anisotropic material. So in practice of doing research, I have to, perhaps if I quickly go back here, we need to be able to generate these images, these waveforms. The reason is because anytime we do an actual scan on a scanner, we don't know what the true stiffness is. So we don't have real world sets of ground truth data. This is very common when dealing with medical imaging applications. When we deal with things like financing, we'll almost always focus on actual real world examples. But with medical results, we need a known ground truth, which we don't get from patients. So instead, I've been using simulated data. I'm not going to spend very much time here on how exactly I'm doing this in the mathematics. But what this model lets me do is plug in a map of what I want the stiffness to be. That's my ground truth. Generate simulated waves, such as this map here. And then we can invert that to get back to a map of stiffness. Because I created that ground truth starting point, I can compare how well our inversion did. Implementing anisotropy into this, I picked transverse isotropy. It's the general form that describes fibers. The reason for this is because we know structures in the body, like neuronal tracts in the brain, muscle fibers, the spine, should all act like it's made out of fibers. So picking a model that assumes something is made out of fibers should match anatomy pretty well. Here's the equations that are governing this. For the model, I also have to implement some additional rotation steps to handle arbitrary directions of the fiber. And I did a bunch of testing to show that that works as I expected. But that's not what this talk is about. This talk is about where we're using AI in this process. So once I had this functional model, I started looking at how well a convolutional neural network could do at estimating material properties of this simulated material I have. One question that was of particular interest is, can we determine what direction those fibers inside of a material are facing? So here I actually showed a test looking at whether or not I could predict, using a convolutional network, the angle of rotation of one of those fiber tracks. And the sort of obvious answer here is, once again, we don't have any other analytical solution. There's nothing else currently implemented that would allow us to get that measurement. And we are clearly beating the null hypothesis, which would be our best case scenario guess. So we're doing better than statistical randomness, and we're doing it in a place where there's no other algorithm that could do it. I include quite a few sources in this, but before moving on to the coding part of the talk, does anybody have any questions up until this point? Yes?
Just real fast one. What is a convolutional neural network versus the other ones?
Oh, good question. A convolutional neural network is a neural network that uses convolutional layers as part of its structure. So I didn't include slides on what a convolution is. A convolution is a way of subsampling data. So if I have a 100 by 100 image, I can use a convolution to instead process something smaller, like a 25 by 25 image that still has all of the same features as my starting image, but will take a lot less effort to process and might give me just as accurate results. So when we look at the neural network in the example, it'll be using convolutional layers that are 3 voxel cubes. So basically you turn every 9 voxels into 1 each time you're going through the neural network to decrease the total amount of computation you need to do. Any other questions? Yes.
Great talk and really novel work. I just wanted to ask, I mean, you're currently using simulated data.
Mm-hmm.
So what do you think would be like a couple of limitations? Because I can see this can be used in practice
Yes.
in the future. So what do you think are the biggest limitations you have that you need to somehow figure out to get to clinical practice?
Yeah, the biggest hurdles to get over whenever you're using simulated data, but also just creating a new algorithm in general, is you have to go through a process of proving efficacy. We have to prove that this works. So the simulated data itself has gone through a number of tests, including going through inversions from our standard analytical solutions that we've been using in clinic to show that it matches with all the results we'd expect. There are repeatability studies where what we've done is we've taken a number of volunteers, we've scanned these volunteers multiple times over a fairly short duration, normally the same day or a couple of days. And in that case, we'd expect most healthy people to stay the same from day to day. And what we can do with that is use those different scans and see how well our algorithm returns the same result on the same person. We can also use phantom data to make sure it's matching what we'd expect from phantoms. And all of that has to be done before you're ever going to get this into a clinical application. I think that's sort of the biggest roadblock when dealing with simulated data and just algorithm implementation in general. Any others? Otherwise, we can, yes.
Just a quick question. This is more generally wave diffusion. If you have objects behind another one, is there any way you can pick up information?
Yes, so all the images I showed here were two-dimensional slices. We actually do this in full 3D. So we can look at any slice from a 3D volume. And actually that's something we'll be able to see in the coding example as well. This is all being done on full 3D volumes with waves propagating generally in your skull from all directions. So you're going to be able to see really everything anywhere, or no matter where it is. It's very difficult to block something off. You need like a sphere inside of your skull with something inside of it that you couldn't get waves to in order to actually block anything. Okay, well, if there's no others, and I don't know how many people were planning on following along with the coding demo itself, it is up on Colab, and I will keep it there so that link will continue to function. But I thought it would be beneficial to show sort of what all the pieces of this actually look like in practice. So this is all in Python for reference. That's just sort of what Google Colab likes to use. And Python is free, and you can run this on anything. So first thing here, we're doing just a bunch of imports. Big things to look for are TensorFlow is a neural network library. What this means is that I don't have to individually write the algorithms for every neuron or structure of neural network I want to implement. You can do that, but I should say if you are capable of writing those algorithms, you should probably just go and apply for a job at Google. I'm sure they would love to hire you to work on their AI. Most people are going to use something like TensorFlow or PyTorch when implementing neural networks and not doing the coding of the fundamental neurons themselves. The next thing I need to do, or we need to do in order to get this to work, is we need some way to generate that simulated data. Now, in my actual research, I use a finite difference model to generate that data, which is substantially more complex than the model I have here. This is a simple analytical solution that lets us just directly calculate what the wave field for a single point source would look like. There's obviously some limitations here. You can't actually use this for like the anisotropic material properties I'm doing in research. But the code I'm running for research, we also could not sit here and actually run all at once here. It would be far too slow. So the main components of this are defining these mesh grids. X, Y, and Z are just grids that have basically they're a distance away from an edge. So your Z1 is how far are you away from your first slice. Your Y grid is going to be how far you are from your top edge. X is how far you are from your left edge. Material properties we're looking at then are frequency, which we can feed into this function I wrote. That's going to be 60 hertz if we're doing standard brain MRE, as well as material properties such as density. And then here we're just looking at two material properties, stiffness and damping ratio. Stiffness is going to affect wavelength. Damping ratio is going to affect how quickly those waves die off over time. The more damping you have, the more quickly the waves fall off. And then T is how long after you initially start oscillating your source do we want to grab a snapshot of this and see the wave images. So I won't necessarily walk through any parts of these mathematics, but if anybody has any questions about a specific part, and maybe since looks like most of you are just watching the screen, I'll try to make this a little bigger and easier to read. And then at the bottom of here, I just call that function twice so that we can look at some examples. And we can see from those examples these wave images that we get out. So we have a single point source located somewhere inside of our volume, and then we can watch as those waves propagate and start to die off over time. So again, this is a simple example, just looking at one wave source and modeling that propagation from a purely analytic solution. Getting then to the neural network. We have to prepare our data in order to feed it into the neural network. So we're going to define how big we want the data set to be. In this case, each data set I'm going to look at is an 11 by 11 by 11 voxel cube. Here, what we're doing is just creating an empty array for the displacements and an empty array for our true stiffness values. When training a neural net, you will have multiple steps of training, but also each step will be a batch of data. So for the number of simulations here, our input, that's going to end up being our batch size. How many examples we want the neural net to look at once. So that's a parameter we can tweak later. Obviously, the more you have it look at, the more resource intensive this will be. Then for each set we need to generate, I am defining a frequency, a density, stiffness and damping ratio, as well as that time after initial onset. These are parameters that we could randomize, and that's something that we can take a look at here and see how that affects training and how that affects our results. But for right now, I'm going to hold these all constant, just so we can see that really simple case of what does the neural net do when all of these are constant. I'm going to use that function from earlier to actually generate the displacements, but then I'm going to make one change to them. I'm going to add noise. So I take some signal to noise ratio and I calculate a noise field and I add that to the data. This is done for a couple of reasons. One, it helps prevent overfitting. If our data has noise in it, the neural network can't as easily learn what a specific data set looks like, because every time it sees that data set, it's going to have different random noise in it. This is exceptionally important if you have a limited amount of data. That data can be limited either due to computation time Oftentimes I'll train neural networks on maybe a batch of 4,000 sets, but those 4,000 sets were computed beforehand because they alone can take a week or two to compute. And then by adding noise, I can effectively take that 4,000 data sets and have them act like a lot more than 4,000 data sets from a training perspective, because they look slightly different every time the neural network sees them. We also want to make sure that the data looks like what we would actually get from a real scan. So a real clinical scan is going to have noise in it, so we need to include that in our training so that our neural network has seen it before. Otherwise, if you start giving your neural network things that it has never seen before, results get very unpredictable very quickly. I'm going to add both stiffness as well as that damping ratio parameter to the outputs of this neural network. So when we run data sets through it, it's going to give us an estimate for both of those independently. And then the prediction matrix, or PredMat as it got called here, is just the set of our displacements. So those wave images with noise added get to be the inputs for our network. And then this is actually kind of just a housekeeping thing of you end up needing sort of one more function here for it to play nicely with TensorFlow. I think I ran that already. Last thing I'm gonna run here, this line, if you're running this yourself, is just there so that Colab can access your Google Drive. That way we can save the weight file from our neural network and load it in later. Otherwise, you just won't have anywhere to save it. So then we get to the neural network. There are a lot of structures for neural networks, effectively infinite, if you allow the size to just scale indefinitely. When we're trying to put together a neural network, we don't want to go larger than is absolutely necessary. The reason why is the larger the network becomes, the more computationally intensive it is to train and also to run. So when we want to get these scaled up, potentially have these run on clinical workstations that aren't always designed to handle large intensive algorithms, the smaller we can keep our neural network, the better. That being said, you don't want to go too small because then you're potentially missing out on things that a larger neural network could do, but your small one can't. So with that in mind, I've actually gone pretty small here compared to what I normally use, with just 10 filters in each one of these layers. We have this single convolutional step, and here our kernel size I call filter size, which I define to be 3. So this is where we're looking at a 3 voxel in each direction cube. So 9 voxels, sorry, not 9, 27 voxels total. And we are effectively subsampling from our 11 voxel cubed smaller regions of 3 voxels cubed, which decreases the total size of the data. It also means that the features we're looking for are not going to be present in 1 voxel. I can't look at 1 voxel of this image and tell you what the stiffness is. There isn't enough information. I need a larger view. So here we're doing 3 by 3. The other thing I've gone ahead and implemented is when you do that, you have to account for the fact that your data set is shrinking. Every time we do that convolution, we end up with a layer of zeros around all of the edges of our data set. The zeros get added there just as padding to keep everything the same size. So I also then have this cropping step where I just take this new data set after the convolution, I crop off those edges, and every time it runs through this for loop, the data set gets smaller and smaller, actually until we get down to just 1 point in the middle, which we then use to give us our outputs. What this means is, for this example, we start with this 11 voxel cube, we push the cube into the neural network, and it's estimating the stiffness and damping ratio at the very center point of that cube. This is something we actually use in practice quite frequently. We'll do patch-based inversions. So we'll take a data set like an MRE scan, and we'll break it into a whole bunch of 11 voxel chunks. those chunks overlap so that every voxel we care about in the inversion is the center voxel of one of these 11 voxel cubes we feed into the algorithm. The algorithm then looks at the surrounding 11 voxels to determine what the center is, and then we just glue all those together. Because you have significant overlap of those 11 voxel cubes, this doesn't end up being a problem in terms of discontinuities or anything like that in the final data set. Then finally define the output. It is important we have to define how large we want that output to be. So here that output has a size of 2. We're looking for 2 parameters, the true stiffness and that damping ratio. When looking then at the neural network, we can define things like what we want the loss function to be. This is the thing that the algorithms are trying to shrink. So in this case, mean squared error is the easy one. Try to simply get as close to the ground truth value as you can using mean squared error to determine how accurate you are. There are cases where more advanced loss algorithms can quite significantly improve performance, or cases like if you hear about ChatGPT or those AIs, where using something like mean squared error wouldn't make any sense when your output is written text. You would need some way to determine how well the written text it's outputting matches what you want it to match. A couple of other things. Here I define a thing called patience. This is how many epochs of training to do before stopping if the losses are continuously decreasing, or sorry, stop continuously decreasing. So that might be most obvious here if I actually start training this. As we train this, and we can ignore the warning here. We can watch the loss, and here these are both the same. So that mean squared error decrease as we train through each one. When we finish 500 data sets here, which is just the number I picked, we're going to finish this one epoch, and then we're going to start another. Oftentimes you do checks between epochs, looking at validation data in order to make sure you're not overfitting. You can use things like the mean squared error of your validation data to determine if you should stop training. There are cases where your neural network can overfit your data, and in those cases, you want to try to catch that early and stop. So once this finishes, and I'm just doing 2 of these here, then we can run through some test examples. So for test examples, all I'm doing is I'm loading in. Actually, I need to change the name of this. I renamed that at some point. So I guess if you're following along, make sure you change the name of this in the version you copied. I'm loading in those weights I just saved out from training. And then I'm just saying, okay, we're going to do 50 test sets. I am using my same make training function I used for the neural net to generate the test sets. We're going to process all of those using the model predict command. So predict on our input data what our outputs should be. And if I go ahead and plot what our outputs look like, we're going to get 2 very boring graphs here. They look like they just have 1 point in them. And that's because all of our examples all had the same stiffness and the same damping ratio. In my training generator, I didn't have those randomized currently. And the result of which is that our neural network was very easily able to learn that stiffness should always be 2, damping ratio should always be 0.6, and all of our test sets match that. So like we'd expect, we see very boring graphs. At this stage, are there any questions? Otherwise, we can look at what happens when this isn't a trivial case and we actually need to predict things. No? Clear as mud? Okay, the obvious thing to do next then is to not look at the trivial case. So the trivial case is every data set's the same. We really don't need a neural network to do that. So instead, why don't we look at a case where we let stiffness vary. So rand here will give us a random value from 0 to 1. And then I'm just going to scale this so we get values between 0.5 and 2.5. I don't want to let go all the way down to 0 because we end up dividing by stiffness when calculating the waveforms. So if we let that go all the way to 0, we'll obviously get errors there. And for the moment, I will just keep damping ratio the same so we can just look at what happens when one of our parameters is varying. We'll run the exact same neural network structure. And if we look at training this time, the only real difference here is going to be that our mean squared errors don't improve nearly as much. Now, we will potentially see mean squared errors that are much lower than what they actually appear to be when we look at the graphs. The reason why is because we have one of our two parameters not changing. That damping ratio is going to be the same in all of our data sets. And the neural net will learn that, and that will help artificially bring down its mean squared error, even though one of our parameters could be way off. Obviously, we could also potentially do a better job of learning this if we used a larger neural network or ran through more training data, but I'm not going to do that for today because, as is, I have to kill time waiting for it to train. Which apparently it is still finishing. I'm not sure why this one's slower here. It should be done. There we go. So we'll do the predictions again. And now when we look at that first plot, what we can see is the neural network is doing a very good job predicting our values. So what I have plotted here is on the x-axis, I have our true values, and on the y-axis, I have our prediction. So in the perfect case, we would get a perfectly straight line where the slope is 1, and all of these match up perfectly. A true value of 0.7 gives us a predicted value of 0.7. That here is very close to what we're seeing. So with just that simple sort of neural net structure, we were able to generate wave images with differing amounts of stiffness and then put in wave images, and we can get out what the stiffness of the images are, even if we don't know the true value. Here I'm just plotting that so that we can see that we are matching it. Any questions at this stage? Yes.
Go back to the training data.
This one or?
You have images of the training data.
Yes. So these are effectively what our training data will look like. The only slight difference, I threw this in though, I don't know if I have anything to find. That one may or may not have noise in it. Our training data will also have noise present in it. So if we go ahead, I think I can just make it calculate those right now. Oh, nope, I don't have. Oh, I have the wrong sizes here. Oh, apparently I did not make that one easy on myself. So yeah, all it's really going to look like is our displacements will look like these images here, but with noise present. So noise is just going to be additional speckling that so this is our starting value here. If we go ahead and add noise to that and look at what that output looks like. We can kind of see what the wave images in that look like. We have our dark region, we have our brighter region, but the noise has added a considerable amount of blocking to this. That makes it quite a lot harder to visually see what's going on in the training data. So every training example that the net is seeing, as well as those test examples down here that are generating this very nice, more or less perfect fit for this case, those are all going to contain this noise as well. So the neural network is handling that and still able to tell you, and this is the part that I think at first is maybe non-obvious, but this is all the neural network is getting for an input. It gets 11 of these images because it gets a volume. But from looking at this, it's able to determine what the stiffness of that material was. Something that I cannot do looking at this. There are some traditional algorithms that could do that as well, by trying to estimate what wave speed across here would be. But what's really cool about the neural network approach is we don't need to come up with equations for what wave speed are and how to estimate wave speed from images in order to have a neural network that can give us these predictions. So in a lot of ways, neural networks are also kind of a lazy approach because they'll just give you whatever it is you're asking for without really having to do anything else. The hard part is making sure they generalize, meaning making sure they actually run on real world data and not just the data you trained it on.
This is one, just to clarify, this is one of the slices, 11 slices.
Yes, so I guess this is slice 10. We could grab a different slice from this. There's no good way to try to show an entire volume, but here's slice 2 of that same data set. So these are all just sort of stacked.
Question if nobody else is asking. So in a real world data now, if we're looking at, for example, I work in pancreatic cancer research.
Mm-hmm.
So I'm thinking if we're looking at data from the abdomens, so the first thing to define is what the stiffness should be. Right? So define what the stiffness should be in a normal range. And then where the pancreas is, and then what the stiffness have changed to.
So you're saying, and this is like something that's already implemented?
No, I'm just thinking if we ever try to do this in practice.
Yes. Yeah, so what we would do there is, and again, this is kind of a this is a very simple model for the wave images here. But yeah, what you would do for that case is you would define whatever that normal range for stiffness and damping ratio are for the pancreas, and then train your neural network on that. We would also want to include examples of an unhealthy patient. So sometimes when we look at just these are the normal values, those end up being normal for healthy individuals, but we need to make sure that our neural net is also going to encompass the unhealthy individuals. The other big thing you probably will want to change is for a lot of anatomy, we want to try to include some structure in the data. Here I'm doing data sets that are just these continuous regions of waves propagating. If we look back at some of these examples here, we see a lot more structure. These are assigned material properties. So we actually, over that volume we give the neural net, have varying stiffness. And that helps generalize, because a neural network, when we're actually running on a patient, isn't going to have a perfectly homogeneous, same everywhere 11 voxel cube to look at. That would be a really easy case. It's going to have this probably unfortunately lumpy and stiff mass.
So assuming you could work with MRI images together as a multimodal situation, so that MRI wise you can get the segments and with the pancreases and
Mm-hmm.
with the mass.
Yes.
So they're well studied and they can segment pretty well based on the.
Yeah, and there's work like that already happening. MRE as a whole has been, at least in practice here at Mayo, going on for quite a while, and has been expanding to lots of other facilities as well. I don't know if we do the pancreas. There are complications with some organs getting enough waves into them. One of the big limitations there actually tends to be patient comfort. You have to consider getting a vibrating pillow pushed up against a patient in a way that those waves actually get to the pancreas, and how we're getting that there. And there's some different options. There's some belts that wrap around that can vibrate from different places. I know liver is one thing that we look at. Brain tends to be kind of a weirdly easy example. You'd think that would be like a hard one because it's inside the skull, but you put that pillow behind the head and it takes very little amplitude before you really see nice waves propagating to the entire brain. So,
Thank you.
yeah, absolutely. Anybody else? Well, if not, I guess that's sort of all I had planned for today. So hopefully I didn't have anyone fall asleep for too long. Yes.
The stiffness parameter that you're talking about, is it basically the same thing as you'd see in any material science definition of stiffness, or is it special to
It's not special to soft tissue.
stiffness?
Yep. No, that is typical stiffness. The only thing I'll say when we talk about sort of typical stiffness is, again, that matrix that defines stiffness can be quite large. We're almost always talking about some simplification. For example, here, when I refer to stiffness, what I'm actually referring to is just the, where's the easy case of this? I'm actually just referring to this single mu parameter. So I'm not really encompassing the entire realm of stiffness, just that one thing.
Anything else? If not, thank you, Jonathan.